You're given this equation and you're asked, what is the velocity of the wave? So the first thing, you have to look at that and say, yes, this describes a propagating wave. And you see that from this argument here, which is of the form omega t plus beta z. So that the equations don't get too messy, the units are not shown for omega and beta, but we know for omega the units are inverse seconds, and for beta, the wave number, it's inverse meters. That way, when you multiply omega by the time in seconds, you get something that's unitless. And when you multiply your wave number by z in meters, again, you get something that's going to be unitless. We know the velocity of our wave is omega over beta. We've already identified omega as 3 times 10 to the 8th inverse seconds, and beta, our wave number, as 2 inverse meters. So our velocity is 1.5 times 10 to the 8th meters per second. So we only have the magnitude of our velocity. So when you're asked for velocity, you want the direction also. So looking at this argument, we see that if time is increasing, z has to decrease so the argument of the cosine function can remain a constant. So that indicates a wave propagating in the minus z direction. So the answer for part A is the velocity is 1.5 times 10 to the 8th meters per second in the minus z direction. Now in part B, you're asked to find the dielectric constant of the material in which the wave is propagating, and you're told that the material is non-magnetic, so that mu is equal to mu 0. You know that this wave is propagating in a dielectric because in free space the velocity would be 3 times 10 to the 8th meters per second. We know the velocity is equal to 1 over the square root of the product of the permeability and permittivity of the material in which the wave is propagating. So for mu, we can substitute mu sub 0, and for epsilon, we'll substitute the dielectric constant times the permittivity of free space. So we can separate this as 1 over the square root of the dielectric constant times the second term, which we recognize is the velocity of our electromagnetic wave in free space, just the speed of light, which is 3 times 10 to the 8th meters per second. For this term to be our velocity of 1.5 times 10 to the 8th, the square root of epsilon sub r must equal 2. So our dielectric constant is 4. So part C is asking us for the wavelength. Well, we know the wave number is equal to 2 pi over the wavelength. And our beta is 2 inverse meters. So the wavelength of this wave is pi meters. In part D, you're asked to find the magnetic field intensity. From our mental model of a transverse electromagnetic wave, we know that the magnetic field intensity propagates along with the electric field intensity. So the cosine dependence is going to be the same. We know that the electric and magnetic fields are transverse, and that they are also transverse to the direction of propagation. So the magnetic field intensity must be in the plus or minus y direction. We also know the units of magnetic field intensity are amps per meter. The next step is to find the amplitude of our magnetic field intensity. We know the intrinsic impedance is the ratio of the magnitude of the electric field intensity to the magnitude of the magnetic field intensity, and that it's equal to the square root of the permeability over the permittivity. So we can substitute our values in for the permeability and the permittivity. So for this medium in which our wave is propagating, the intrinsic impedance is half the intrinsic impedance of free space. Our intrinsic impedance will be 188.5 ohms. So the amplitude of our magnetic field intensity is 1. So here's what we have so far for our magnetic field intensity, but we have to check one more thing. We know our wave is propagating in the minus z direction, so our power flow has to be in the minus z direction. So E cross H has to point in the minus z direction. Our electric field intensity is in the plus x direction, when our magnetic field intensity from this equation is in the plus y direction. So A sub x crossed with A sub y is A sub z. So this would indicate power flowing in the plus z direction. So we have to insert a minus sign here so that when our electric field is in the x direction as stated in the problem, the magnetic field intensity is in the minus a sub y direction, so our cross product of E cross H gives us power flowing in the minus z direction. So here is the answer to part D for our magnetic field intensity for this given electric field intensity.